I was supposed to do this together with Rianne, but unfortunately she couldn't make it today. Very long story, but I'll just leave it. So you have to do with me. Sorry about that. But Rianne is here in spirit, and she has contributed a lot to the stuff I'm going to talk about. So just a little bit about me. I couldn't resist. Who am I? I'm a very old guy. I used to do this stuff before you guys were born, I guess. Some of you. I don't know. I guess nobody was born after 2000, right? Anybody? Yes. Wow. So you were born after I had my first UAI paper.
Do I even have a chance in this field?
Well, that's actually what I thought in 2000. So, then I had several UAI papers. In 2010, I was the chair of UAI, so UAI and me really have a history. That was in Catalina Island. It was an amazing place. I think this is also kind of an amazing place. And then I was the general chair. But then in 2019, I figured I discovered all this stuff about e-values, and some other people did as well, and I figured I really want to focus on that. So I kind of left the machine learning world. Having said that, UAI was less a machine learning conference than it is now, actually. In 2000, it was actually really nice. It was a very general, like you could speculate about all kinds of AI there. Very nice. But now e-values are coming back to machine learning. So I'm back, and indeed we'll have a workshop on e-values at NeurIPS. So in case, I don't know if some of you are actually working on e-values, this will be the first workshop on e-values at a major machine learning conference, I think. And you have 2 more weeks to submit something, but it's going to be a very light reviewing process. Yes, so that's the history. And then, of course, the reason I'm here is because e-values are coming back to machine learning, but also because I live and work very close by. The CWI is basically a 20-minute walk from here. Okay, so where do e-values come from? Before I'm going to define them, let's give a little bit of history. So in some sense, it's not such a new concept. It's already appearing implicitly in work on Harold Robbins, who was a famous mathematician at Columbia University, and his students. And then in Russia, they were independently kind of discovered. But then not very much happened until suddenly in 2019, that's kind of when I said, like, when I decided to focus on e-values and also anytime valid inference. And suddenly, within the course of just like 5 months, there were 4 breakthrough papers arrived on arXiv, which are now all in major statistics journals. So there was our own paper, Safe Testing. We actually call them S-values. It was the first paper that actually gave them a name. And then we decided with the other authors a few months later to decide on the name e-values. But you will still see in this tutorial, I will use the abbreviation S. That's a little historical thing. I like to use that word, that letter. Well, you had these other papers, and then things happened very fast. And so like now we had like 4 international workshops. There are literally hundreds of papers, mostly in statistics journals, but also, goedemorgen, hi. But also in more and more at NeurIPS and Cold and so on. And so they are about the general field of e-values. The other buzzword is anytime valid inference, anytime valid confidence intervals, testing by betting, optional stopping. So if you go away with an idea of what all these things mean, then I have kind of accomplished my goal. So before I go really into what it's all about, a little bit more about the people behind it, history. So if you want to know about this area, then the name to know is the name of Aditya Ramdas. I guess many of you have heard about him. He's a very celebrated, famous young machine learner statistician. He writes a paper about this almost every week. Even before chat came along. Nobody knows how he does it because the papers are actually very good. Then, as a distant second, but still, my group at CWI, and that includes, for example, my former student Rianne, who's now in Twente, also publishes quite a lot about it. And then there are more and more other people all around the world writing about it. And there's one name I really have to mention here. That's Volodya Vovk. So Volodya Vovk is basically the only one in the world who wrote about these things between 1976 and 2019. It's a bit of an overstatement. So that's really kind of a pioneer. And what's really interesting is that that's actually the first paper where e-values were used in a practical context. That was at UAI in 1998. Does anybody know what that paper was about? So e-values, they were called measures of impossibility, and they appeared only on page 4 or something. That was actually the paper that introduced conformal prediction, same paper. So modern e-values and conformal prediction were introduced in the same paper. Nobody got it. Actually, I remember at the time I didn't understand a word of that paper. And 2 papers later, Volodya decided to use p-values instead of e-values in conformal prediction because nobody understood this, what he called measure of impossibility stuff. But it's interesting that they have kind of the same root. You can do conformal prediction. I won't talk about that both with e-values and with p-values. Okay, so that's kind of the history. So now a bit about motivation. So let me ask first, is there anybody here who has never seen the definition of an e-value? Okay, there are quite a lot of people, so don't worry, we will go through it. But then it's good that I'm going to really start from scratch, from the beginning. Where do these things come from? Well, you should think of them as an alternative to the p-value. They measure, they are a measure of uncertainty, of evidence against a certain null hypothesis. So you have a hypothesis. You want to see whether a medication works. The null hypothesis it doesn't work. You test it on several participants, and then usually you have the p-value, which measures evidence against the null hypothesis that the medication doesn't do anything. Instead of that, you can use an e-value. And just like with p-values, you can use e-values to create confidence intervals, which gives you a more general assessment of uncertainty. So why not just use the p-values? Well, I guess that is something all of you have heard about. They are wrought with problems and issues. There has been lots of discussions about whether we should even use them. Here you see some papers. It was mostly 10 years ago. There were lots of papers. So here's the American Statistical Association telling people that a small p-value doesn't really mean very much. And of course, it's not. So what does it mean? Not so clear. And there are all these things called the reproducibility crisis, where they try to reproduce studies, both in medicine and in the social sciences, where they found that they were done these were studies done with the highest standards. So you have a null hypothesis, whether some effect exists, that some effect does not exist, you test it, and then you find a small p-value, so you reject the null, you say the effect exists. And then they do reproducibility tests, and then half of these studies, which at first had really small p-values, still fail. So in the new test, you cannot reject the null hypothesis. And that was kind of associated with problems with p-values. So then many people said, yeah, but you shouldn't use p-values, you should confidence intervals. But that's not where the issue lies, because they have the same issues. Maybe some issues go away, but that's not the issues I'm going to talk about. They are inherent both to p-values and to confidence intervals. So I'm going to focus on one of them, which at that time was not really highlighted, but that's kind of where e-values have their biggest. They have 2 big claims to fame. There are 2 things they can do much better than p-values, and this is one of them. So suppose we test some medication and we get a promising but not conclusive result, like a small p-value but not super small. Say p is 0.04, which usually you can publish if p is smaller than 0.05. But this is a bit smaller, so maybe you can write a paper about this, but it's also not super exciting. So then another group tries again whether the medication works on new data, maybe new patients. And then maybe you still get a p-value in this area. And then, well, maybe we want to get even more evidence. So another group, maybe in a different hospital, tries the medication again on new data. And now the question is, how should we combine these results? This is, of course, this is not the exception in the medical world. Maybe, the AI world is very different, but in the medical world, this is the standard. If you think about, for example, the medication, the question whether corticosteroids help against meningitis, that's inflammation of brain tissue, I think. There have been more than 30 randomized clinical trials over the last 30 years, each of which costs maybe a few $100,000 or euros, and they still don't know. So this is the way science is done these days. You test, you see, well, maybe you do another test, etc. And then, of course, you want to do a meta-analysis. You want to test, combine the results. And what then people do more often than not is they put all the data together and recalculate the p-value for the joint data. And if you think about this, this is not correct. If you look at the definition of a p-value, you see that you're not allowed to do this. If you do this, what you get is not a valid p-value anymore. In a moment, we will see why. So this is basically p-hacking in a way. Maybe not done on purpose, but still. But then if you look at meta-analysis, before there were e-values, the question is, do they have better tools to do this than just throwing the data together and recalculating the p-value or other statistics? And the answer is no. There was not a real way to do this and still have things like error guarantees. I will make that precise, all of that precise in a moment. Actually, I'm going to make it precise right now. So here we have the notation I'm going to use throughout this tutorial. You have some null hypothesis. For example, this could be the set of all normal distributions with variance 1, very simple case. It could also be non-parametric, we'll see that in a moment, but I always use this theta notation just so I can speak about names for hypotheses. Sometimes, not always, I'll also have an alternative hypothesis. My data vector is denoted as x and then superscript n. And now, a classical test, the way statisticians do testing, is their null hypothesis would be, for example, the mean of a normal distribution is 0. And the alternative would be it's not 0. So it could be either the mean is larger than 2, or the mean is larger than 1, or it could also be anything but 0. It really depends on your application what you want the alternative to be. But now, for now, actually only the null is really important. So the null is just the mean is 0. How do you test? Well, you get some data, and then you're going to reject the null, conclude something is going on, the medication might work, things like that, if you see something which is quite unlikely under the null. So the standard way of doing this, if you test a normal, that's called the z-test in statistics, is you look at the average of the data, which is also the maximum likelihood estimator for normal distributions, and you reject if that is larger than 0. If you do a one-sided test, if it's larger than some value, and here we're going to do a two-sided test if its absolute value is larger than something. And you usually do that. This is kind of the standard thing. You take it if you reject if it's larger than 1.96 over square root of n. Why do you do that? Because the average will itself have a normal distribution under the null with mean 0 and square root and variance 1 over square root of n. And this is the area which has 5% probability in the tails on the left and on the right. And so that's equivalent to saying I define a p-value, which is in this you can define it in many ways, but the standard way is to define it as the area under the tails on the left and the right together, equally large tails. And you reject the null if the area under the tails is 5% or smaller. That's equivalent to saying the average is larger than 1.96 over square root of n. This is how we do it in the standard way. If we have a 5% significance level, so what we do, and this is called the Nyman-Pearson test, it's the classical way of testing, you fix this alpha in advance, typically 5%, and then you reject the null if your p-value is smaller than alpha, which means that you're so far in the tail that you've observed something which under the null would have a probability of 5% or even smaller. Another example is the t-test. That's, even in this age of AI, apparently the most widely used test in the world. It's the same thing, but now you don't know the variance. So the variance is now a nuisance parameter, and this means that the null is now composite. It's a set of distributions, one for each variance. And what I want you to remember for now is I'm going to work with simple null for now, but keep this distinction in mind, because that's going to be super, super important. There's a very intrinsic distinction between simple nulls, composite nulls, where this variance can, for example here, the variance is unknown to the person doing the test. So p-values, you can define them more abstractly like this. I've just given the standard way to define it for normal distributions, but the standard definition is simply a p-value is something which, if the null hypothesis is true, there's a small probability that it's small. That's a very kind of self-referencing distribution. So the probability under every distribution in null that the p-value is smaller than alpha has to be smaller than alpha. This is the general definition of the abstract mathematical definition of p-value. Usually we have this even with equality. It's not necessary for the theory. It's not an important distinction, but with this normal distribution, when we rejected, when we were out in the tails larger than 1.96 over square root of n, that p-value corresponds to basically the probability of being in the tails. The probability that the p-value is smaller than 0.05 is exactly 0.05. But sometimes it's too difficult to make p-values with that property, and then it's enough if they're smaller or equal than 0.05. For example, if you have discrete data. So why would you do all of this? Well, the basic idea is that, that was Nyman Pearson's idea of the 1930s, that no matter what you do, there's one thing you want to make sure: you don't want to have a large type 1 error. What's a type 1 error? That's the probability of saying there's an effect, saying the medication works while it doesn't work. So that's the probability of rejecting the null. They just use this terminology: you reject the null under the assumption that the null is true. So they say, whatever we do, we want to make sure that this probability is smaller than alpha. And then among all procedures that achieve this, maybe we want to have the one which is small type 2 error as well, which is the probability of accepting the null while it is wrong. That should also be small, but this goes first. You can think a lot about that, but that's just what they did. And of course, if you do this procedure, which I just described, then you will have this property. You will have that because you reject if the p-value is smaller than alpha. Well, the probability that the p-value is smaller than alpha is smaller than alpha. So the probability that you reject if the null is true is smaller than alpha. So now I claimed before that things go wrong if you do this, what I call optional continuation. Like you look at the data of a test, p was 0.04, and let's do a second test, and then combine the data. So you have your first test, you observe, let's say, 100 patients, or 100 outcomes of normal distribution, and then, let's say, if it's significant, you reject the null and you stop. But otherwise, you do a second test on a second batch. And if that is significant, let's say we do this only in 2 rounds, then you reject again, and otherwise you accept and you also stop. Of course, in practice, this can be done for a lot more iterations. You can do a 3rd test and a 4th test, and also the rule of like when you stop and when you go on to a new test will be murky. Nobody really knows what somebody looks at the data, says, well, I have some money to get new patients. Let's look at new data. But this is kind of idealized. In practice, it will be more complicated than this. But let's see what happens in the idealized scenario. Well, if you have a strict p-value, which we had, so the probability that it was smaller than 0.05 was exactly 0.05, then the probability that you reject at stage 1 is exactly 0.05. So what happens here is you do this first test, and let's say the null is true. So there is no effect. The mean of the normal distribution is 0. You do your first test, probability that you reject is 0.05. But here you have an escape route, because there will be some data for which you don't reject the first time, but you give them a second chance. And of course, then you will put it together with the first data set. So maybe the second chance that you reject is not very large, but there is an additional chance that you reject. So now the probability that you reject the null in this procedure is larger than 0.05. It's actually 0.055 or something. You can calculate it. But this means that your procedure doesn't work anymore, because you're promising, that's the whole, everything behind Nyman Pearson is about promising this type 1 error of 0.05, but you're violating it. It's larger than 0.05. And the reason is actually, if you would have known in advance that there would have been 200 participants, you could have calculated the p-value for that. But what happens here is that you sometimes have 100 and sometimes have 200. So what you would have to do really is do a p-value which takes into account for some data I will stop at 100, for other data at 200. That's going to be very complicated. And in practice, of course, you often don't know, like under what circumstances you would have stopped at 100, and maybe you will also go on after 200, etc. And all of that is problematic for the p-value approach. Statisticians actually call this, you have spent your alpha. Your alpha was 0.05, and you spend it in the first round, so then it's over. You cannot do anything like go on under certain circumstances. Was there a question? Oh, no. But at this point, old-fashioned statisticians often say, like, well, you know, you just shouldn't do this. It's cheating. Or they say, well, we have these methods called alpha spending, which can kind of account for that, but then you have to say in advance, like when you're going to look at the data and so on. So you spend it in several rounds. I've never been convinced by that. Of course, I'm biased. But the reason is, and now we're getting, for me, what's kind of the heart of things, what really got me into this. In some sense, this is worse than you might think. And here's the example that shows that. So let's say in the first test you have a p-value which is small, but not very small, 0.11. And now you tell your boss, yeah, no, it's not significant, but it's kind of promising. And now your boss gets all happy and says, well, we're close. Let's get some additional data and see if we can get a significant result. And now you are worried. You're a statistician, so you know this is wrong. This will invalidate your type 1 error. But then you tell, well, it was actually not so small. It was 0.11. Then the statistician changes her mind. Not the statistician, the boss changes her mind and decides that you should stop after all because this is not so promising after all. I don't want to risk more money on this. Let's stop. And now the question is, should you be relieved? And the answer is no. And this is really funny. The problem is that the validity of p-values depends on you being 100% sure that the protocol you instated in the beginning would have been followed, no matter what would have happened. So even if on the data you observed you followed the protocol, if there's even the remote possibility that on some other data you wouldn't have followed it, your type 1 error guarantee is already violated. So it's super brittle. I mean, philosophers sometimes say, well, we should ditch the whole thing because it relies on counterfactuals which are kind of unknowable. In practice, you often cannot really know what would have happened if the data had been different than they actually were. But even if you don't go so far, it does show that things are brittle because in the end, you would like to have procedures which can kind of stand this, that if the data had been different than they were, people would have done different things. And this is where the e-values come in, because they don't have this problem. Well, this is a bit of a provocative slide. With e-values, you can do this without any problems, by just multiplying. So you get e-values instead of p-values for each batch of data, and you can just multiply them. And the product will remain an e-value, even if the decision to go on to a new batch depends on the data in the previous batch. And that's even more important, even if you don't know what the dependency is. So your boss might look at the data and says, let's do a second hypothesis test on a second batch of data. And you don't know why your boss said that, right? Your boss looked at the data and decided that, but you don't have to know the rule. Like, did the boss say it? Did the boss have in his mind, like, if it's larger than 0.1, I'm going to go to a next test, or if it's this and this, you don't need to know. It's still valid. Well, then it, of course, solves also some additional issues. The counterfactuals, I already talked about that. A very important one, which I hope to have time to talk about the last half hour of this tutorial, is that practitioners don't understand this idea that you have to fix alpha before seeing the data. And I understand that they don't understand it because it's weird. And you can solve that to some extent, I have to say, to some extent with e-values. They're much easier to combine than p-values, which makes them very much useful in multiple hypothesis testing if you have like millions of hypotheses at the same time. And you need to somehow combine them, and there can be big dependencies, and they're also easy to interpret. At the same time, they're not a miracle cure, so this talk is, of course, a big advertisement, so you should not always take me completely seriously. There are still some issues like some issues with hypothesis testing and with uncertainty are just inherent in the way we do things at a deeper level, and they don't solve them. And also, I was talking about p-hacking, but you can also do e-hacking, and I've already even seen people doing it. So I don't have time to explain to you how it's more complicated, but you can hack anything basically. So okay, so what I'm going to do now in this tutorial is first give a high-level overview. So you've already seen the first bit of that up until, say, we're now here. So now I'm going to go into the math, talk about e-values and the related anytime confidence intervals. I'm going to compare them to Bayesian intervals. And I want to say a little bit about how they compare, how well do they work in practice. And then I'm going to talk about the details, in particular about how to interpret them in terms of sequential betting. That's really, if you get that, then everything becomes so much easier, because then you have kind of a hold, like you know what everything means. And I'm going to first talk about very simple situations, completely unrealistic, like simple versus simple testing, but then I'm going to talk about composite alternatives, composite nulls, non-parametric settings, etc. And then at the end, I'm going to talk about this changing alpha business. So first the overview. So first I'm going to talk about e-values and the corresponding tests. So this is the one, so I know there are some of you who haven't seen the definition before. This is the one thing you should remember. An e-value is a non-negative random variable or statistic, a function of the data, then you call a random variable statistic, such that for all distributions in a null, its expectation is bounded by 1. So we'll try to be kind of consistent and talk about the random variable as the e-variable, and when it takes a value as the e-value. But just like they do with p-values, it's sometimes much easier to just talk about e-values, and even if they're variables, so they haven't been realized yet. So few important things. So if we have a simple null like the z-test, testing a normal distribution, whether the mean is 0, for all p0 means just there's some distribution. So for the normal with mean 0, this expectation is bound by 1. But for the t-test, this is really has to be hold for all the variances, for everything in the null. Second thing is that the constant function 1 is an e-value. So, and that's the same with p-values. They're good and bad e-values. And bad e-values would be e-values that don't even listen to the data. So we will have to talk at some point about what are good e-values. So for now, we'll just do it intuitively. An e-value that always takes the value 1 is not a good thing. But we will get there later. Like, what does it mean to be a good e-value? So the E stands for evidence and expectation. Expectation you can see here. It's just the expectation of something is bound by 1. And evidence is because we will use it to give evidence against a null hypothesis. So how to interpret this? Well, the first interpretation is a p-value after all. This sounds weird. I was just bashing p-values. But you can think of e-values as p-values, but they're very special p-values. They have a special property. If I have an e-variable and I take its reciprocal, then this becomes a p-value, which means, but it has wiggle room. So I said before that for p-values, so we have this 1 over the e-value, the probability that it's small is small. That's the definition of a p-value. But for p-values, we usually had equality here, or near equality. And for e-values, if you take 1 over them, we have a strict inequality. And there's usually quite some room. They're more conservative. And this is what's needed to make them work for optional continuation. We will see this is kind of also a price to pay, because you sometimes need more data to get to the same conclusion. Another thing to note here is that large e-values are evidence against a null, because a large e-value corresponds to a small p-value. Why is this so? Well, basically an e-value is non-negative and it has a small expectation. So then clearly the probability that it's large has to be small. And that's just Markov's inequality. Probability that this, I usually take 0.05, that the probability that the e-value is larger than 20 is bounded by its expectation over 20. That's just Markov's inequality. And because by definition this expectation is bound by 1, this is smaller or equal than 1 over 20. This just proves that this is a p-value. This is Fisher, the champion of p-values. I show him here because who knows, maybe he would have liked it after all, because in the end it can be interpreted as a p-value. Because it can be interpreted as a p-value, you can do testing with it, just like you do with p-values. Namely, you look at the data and you see, is my e-variable larger than 20? And if it is, I reject the null, if I set alpha to be 0.05. Then I have the type 1 error bound of 0.05 of alpha. This is Nyman, the champion of the type 1 error. Who knows? He might have liked it as well, because you can use it for classical Nyman-Pearson hypothesis testing. But there's also a relation to Bayesian testing, which seems quite different, but still, there is. How do Bayesians test? Well, perhaps the standard way is to do a base factor test, where you have, so you associate, you have your null and your alternative, and you have a prior for both of them. That's like a prior for the distributions inside the model. So for our alternative would be all normal distributions, we put a prior on the means of the normals. And then we can get the marginal likelihood, so these are these integrals. And we just take the marginal likelihood ratio. This gives you the evidence for the alternative and against the null, according to Bayesian. Why do they have this formula? Well, basically, if you would have a uniform prior, meta prior on the null and the alternative, this would be the posterior odds ratio by Bayes' theorem. So this would also give you the posterior odds, not probability, the probability ratio between the alternative and the null. So how is this related? If the null is simple, then it's just one distribution. We had that in the normal distribution case, right? It was just mean 0. And then there is no prior within the null, right? All distributions in the null, there's just one, so you cannot put a prior on it. And then the base factors look like this. If we then look at its expectation under the null, we get this integral, and we get this cancellation, density of the null according to this distribution. You divide by it, so this cancels, and you get the integral of a probability density, which by definition of a probability density is 1. So the base factor, if the null is simple, is also an e-value. This is Jeffreys, who championed base factors. So in the 1930s, he smiles. Maybe he would have liked it after all. I picture these three people because they are kind of the three people who created modern testing, and they disagreed about everything, but in a sense, this is kind of a bridge between the three approaches. However, it's super important that we have a simple null here. If we get to composite nulls, this is not true anymore. And then we will see that in general, base factors are not e-values anymore, e-variables anymore. Another thing to remember here is this cancellation. So that there's this basic expectation of S is 1, the definition. This is something you really have to remember. And this cancellation argument that comes back all the time in e-value theory. If you take an expectation of a likelihood ratio, where in the denominator you have the data generating distribution, you get 1. So how do these things solve the optional continuation problem? I'm not going to give you any proofs of theorems yet, but just give you an idea. So let's say we are in this optional continuation world where we get batches of data. So each y could be a sample of x1 to x100. That was what we had at first. Or it could itself be given by a z statistic, like a summary of data or some unordered data, and anything goes. But let's think for concreteness that it is itself a data vector, as we had before. So what you do is you first evaluate some e-variable. So it's a function of the data on the first data. And if the outcome is in a certain range, for example, your boss likes it, then you evaluate an e-value on the second batch of data, and otherwise you stop. But for the second range, you could do the same thing. For the second batch, you could do the same thing. If that is in a certain range, so you actually compute a third e-variable, and otherwise you stop, and so on. So let's say you do this several times, maybe 25 times, and in the end you do stop. And then you report as your final result the product of all the e-variables so far. So the number of times you do is tau. And what's important here is that tau is random. It's, if you know martingale theory, it's actually a stopping time. It's itself a random variable because it may depend on the data what it is. And the first insight, I'm going to make it, give an intuitive proof later, not a formal proof, but for now you will just have to believe me that the product, if you do this, then the product you get is itself an e-variable, no matter what the rule for optional continuation was. So you don't need to know what this rule is. Your boss might have implemented it and you don't know how, or you could have done it yourself and say, I want to stop as soon as the product is larger than 1 over alpha. It's all fine. This product will itself be an e-variable. And this means that once you stop and you reject if the product is larger than 1 over alpha, your type 1 error is still bounded by alpha. Still you have to set alpha before, of course. But you get here a type 1 error guarantee, even though you had different batches of data and you didn't know in advance how many batches you would have. And it's important to know that to implement the procedure, you don't need to know the definition of the stop and continue rule. You only need to know if you actually stop or not. So this is a very subtle difference. Sometimes it's you who says, like, I'm going to do, I just want to show that this medication works. So I'm going to do, I have a lot of money, so I'm going to do an experiment here until I get a product larger than 1 over alpha. Then you know the rule, but it could also be that your boss decides after every batch whether to go on or not, and you don't know the rule, and you don't need to know that. What you do need to know is when you stop. you need to know that you actually stopped and then calculate the product. But what the rule was for stopping, you don't need to know. So this solves the optional continuation problem because you still have a type 1 error probability even though you have this optional continuation. But there's more. This is a third thing to really remember. There's something that is actually much older than e-value theory because it comes from martingale and gambling theory. It's called Wills inequality. If you do this, then, and if the null is true, then the product that the probability that you will ever reject is bounded by alpha. So you keep going on, and this is what I said, like this is something which happened in psychology, for example. Also around 2010, there was this famous professor from Cornell who really wanted to prove that people would have certain psychic abilities. And he kept doing experiments like for all his career, and at some point he got one where he had a significant result. But if you would do it this way, you multiply all those results, and the probability that that ever would happen is small. So it's not just in particular when you stop, but you can keep monitoring at all times, because if the null is true, you will with high probability never exceed the threshold. So you can do what people say continuous monitoring. And the proof, I'm going to go to that later today. I'm actually going to lead you to some kind of intuitive proof, but already give you a taste. The reason this holds is because everything in the e-value world, everything we do there can be reinterpreted in terms of sequential betting. And e-value is, in a sense, a bet where you don't expect to get more out of it than you put in if the null is true. So if you do get a lot out of it, that gives you an indication that the null might not be true. And this product is basically how the total amount of money you have if you keep doing sequential betting under bets where you would not expect to gain any money if the null is true. Again, I'm going to explain it in detail later. And Wills inequality is really the same, it's exactly the same proof as the result saying that if you go with 10,000 euros to a casino, the probability that you will go home with 200,000 euros is smaller than 120, no matter what your rule is for. You might say, okay, I've seen now 3 reds in a row. That means I have to go to table 3, or that if I see this, I should go home. Doesn't matter what your rule is, you will not make money. Probability you make money is small, which is very intuitive, of course, and it's also true. And that's just this. So the whole e-value world can be reinterpreted in terms of this sequential testing. Indeed, one of the papers that started in 2019, as I showed you, was called Testing by Betting. So a bit more about this optional continuation. So when we do this sequentially, then for each batch of data, we have to calculate a new e-variable. So that's a function of the new data. So it should, of course, be a function of new independent data. Otherwise, you could recalculate the same e-variable and then it would automatically grow. So that you have to look at independent data and calculate e-variable on that. Think of it as a base factor, for example. So here we have a simple null and we have a base factor which uses their e-variable. So we can now do several things. We could, if we use a base factor, then in the first batch of data would look like this, right? We've already seen that. And then we could do the same, use the same base factor, but apply to new data in the second batch of data, and then multiply. That's one option. But the choice in the next batch of data is of the definition of our e-variable is allowed to everything that we've already seen. You can always condition on everything that happened in the past. So you could also take as your second e-variable, for example, you could take as your prior the Bayesian posterior of the first batch of data. And if you would do that and you multiply the two e-variables together, then you get, well, if I'm assuming your data are IID, then of course in the denominator you get the product of this, and in the numerator you get, by Bayes' theorem, just the Bayes marginal distribution for the full data sequence. So this means that with simple nulls, also this multiplication is consistent with Bayesian updating. Right? We're not doing something which, from a Bayesian point of view, is crazy. What is different is that we don't say in advance you have to use the posterior from the first sample. In practice, you might want to do that. So for example, if you get a new sample of patients to test a medication from the same hospital, you would probably want to take your posterior from the first sample. If you go to a new hospital with different population characteristics, maybe in a different country, you might want to use the same prior again as for the first, because you might have learned some things which are not really reflected in the new data, or you could use a different prior. That's all fine. Because notice that's also important, so this type 1 error guarantee, it doesn't depend on this prior we have for the alternative. You can use any prior you like. Some priors maybe give you a lot more statistical power. They will work better. You'll get, if the null is wrong, you get higher e-values. But if the null is true, you will not reject it no matter what prior you use there. So you can be kind of half Bayesian. You can be Bayesian on the alternative and still have this very frequentist type 1 error guarantee. So this was about simple null. And in a way, all of this was kind of known before 2019. It was just not going on with this terminology. But now we go to composite nulls, like the t-test. And now things get tricky, because the base factor now is not necessarily an e-variable anymore, because the e-value would require that for every distribution in null you have this expectation bounded by 1. But for a base factor, you don't have this. What you have is that if you would sample from the Bayes marginal distribution, then you get this cancellation again, right? Then you have a distribution under this, and then you have this distribution divided by this distribution, and they cancel again. But so here we are really frequentists. We like to use priors in a pragmatic way to guide the direction we're going and so on, but we want to have the hard error guarantee of a frequentist. No matter what distribution in null is true, we should, if it's true, then we should have a type 1 error guarantee. So here we see that things get different from Bayes. And what happened in these 2019 papers was, to a large extent, saying like how to do this e-values, this sequential updating with type 1 error guarantees in generic ways to do with composite nulls. And then you can look at things like the t-test, which are still very simple. You just have a variance in the null which you don't know, but you can also look at non-parametric examples. We see one example in a moment where you could have all distributions with a given mean in the null. Then there are lots of interesting results came out. So one of them, which we'll also see later today, is that actually if you have two parametric models, then if you give me a prior on the alternative, I can make a special prior on the null for you, which depends on the prior on the alternative, such that if I plug in that special prior there, I do get an e-variable after all. So then the expectation is bounded by 1. So, and these are even like, you get very good e-variables, but then, and that's also something we need to do later, we need to define what do we even mean by a good e-variable. Informally, it means that if your alternative is true under the null, it should stay small. It does, by definition. Under the alternative, it should grow very fast, because if the alternative is true, you want to reject the null. You want to find there's an effect. So you need some way of making that precise. Okay, maybe before I go on, I should ask if there are any questions. Yes?
So we have a question about the procedure. You said that the fact that you do need to know when you stop, that you stop, right?
Yeah?
What exactly do you mean by that? Because you also say that you can keep going, right?
Oh, that's a very good question, yes. It's like you... well, maybe let's say you don't even need to know that you need to stop. This is you can do continuous monitoring, and you always have the probability that there ever will be that you will ever reject if the null is true is small. So in that sense, you don't even need. You can look at any time. What I really meant is that you. Yeah, so the thing is, maybe this wasn't a very good slide, because what I used to give tutorials like this, and then I said, well, you don't need to know the stopping time. And then people said, but if you don't know the stopping time, what are you even doing? You just look at the data and don't know if you now should look at the e-value or not. I said, no, of course, you do have to know that you want to look at the e-value. What I mean is you don't have, so the important thing is you don't have to know the rules for determining whether you look or not. So you can kind of forget about the fact, you just don't, that's the only thing you need. You don't need to know anything, basically. You can just keep looking. Yeah. Any other questions? Do interrupt me, because I know that this is going to be a lot of material thrown at you. So until now, I looked at the batch level, right? I looked at different batches of data, and you had an e-variable for everyone, and then you multiplied them. Now, in principle, you could also do this at an individual data point level. The reason we don't always do that, I will get back to that later, but in many cases you can. So what you do then is that you get data in a sequential stream, and at every point in time, you calculate an e-variable for that data point. So it's a thing that only listens to that data point. It's a function of the data point. It's expectation bounded by 1. It's non-negative. And then to get evidence against the null hypothesis, you just multiply all these e-variables for every data point you have. And again, just as before, we said, like, okay, you can use this Bayesian posterior, for example, in your definition. So the definition of your e-variable is always allowed to depend on the past. So a nice way to formalize that is saying, well, your e-variable is actually allowed to depend on past data, just not on future data. So at every point in time, you use a past conditional e-variable, a function from the first I data points to the positive real, such that given all the past data points, this function has expectation bound by 1. So what really happens here is that you have a function which expectation bound by 1, and different paths can make the function on the last one different. That's the way to interpret that. But this is a lot more general, because now you can see that you can deal with dependent data as well. If you define it like this, then you can make e-variables also for dependent data. If we do this on the data level, then we can actually do something wilder than optional continuation. We can do optional stopping. What's the difference? This is kind of just a terminological thing. It means that you can stop at any point in time. Until now, I looked at cases where you have a batch of data. You cannot stop inside the batch, but you can stop in between batches. Now, if we define things with batch size 1, then obviously we can stop at every point in time. So now the idea is you get a stream of data. Maybe if you do a new experiment, the stream just continues and you can stop whenever you like. And now we have Veal's equality again. If we multiply all these e-variables, then the probability that they will ever get large is small. The probability that the product ever gets larger than 20 is smaller than 0.05. Now, this product of these past conditional e-variables is called an e-process. If you know martingale theory, you will find it maybe a strange name, because you will recognize this. I don't know. Are there people here who know about martingales? Like, okay, not many. Good. Then I don't have to be too careful. In martingale theory, you call this a non-negative supermartingale. An e-process is something more general. I will call it an e-process here, because that covers more general things, which I'm not going to go into here, but it's a more general notion. So examples, the e-variables we defined so far are actually also e-processes. So we could have looked at basically at a sample size one batch basis rather than a big batch basis. For example, if you look at this base factor with a simple null, you see that you can, for a whole batch we use this. You can write that as a product of these conditional distributions. So this is the base posterior predictive distribution given the past. And this is the distribution of the null, the ith outcome given the past. If you multiply these, this is well known, you get this. So, so we have this product of e-variables, which depend on the past, and the product is itself an e-variable for n outcomes. Until now, we looked at the e-variable for n outcomes as one thing, but now you see you can decompose it as a project. In general, this is not possible. For example, if the batch comes to you unordered, you get, which often happens, right, in medical data, if you do a meta-analysis, you just get a z value, which is kind of a summary of the data. Then you cannot decompose it anymore. You lost that information. And there are also other cases where this is not possible. But everything we've seen so far, you can go from the batch also to the individual. Now, once we've done this, I can give you a very non-trivial example. And this is actually, this is something where e-values really shine. It's still very simple, though, of a testing with optional stopping, where the null is actually extremely large. So it's composite. It's not but it's not just a t-test. It's the set of all distributions on a bounded outcome space with a given mean. So let's say you have. This is actually also a problem which occurs all the time in practice. People then often use a t-test, which is a bit strange if you know the outcome set is bounded. So you get IID data between -1 and 1, and you want to test whether the mean is 0, for example. You could also do a one-sided test whether it's smaller than 0, maybe more realistic, but keep it simple. We want to test whether the mean is mu. So there was a paper by Woodby, Smith, and Ramdas where they did this with e-values, which turned out it really worked better than, even for fixed samples, than classical approaches. And it worked a lot better than non-parametric based approaches to this problem. So how does it work? Well, you first start with an e-variable for one outcome, as we did before. Like, what if you have an e-variable for just one outcome? You want this expectation under the null, bounded by 1. Well, you just make this e-value. You fix some fudge parameter lambda. Let's keep it some fixed number. And you set it to be 1 plus lambda times x minus mu. Now, and you make sure that lambda is such that this is always positive. If it's always positive, that's one condition for being an e-variable. If you have this, then the null says that the expectation of x is mu. So the expectation of this thing is 1 plus lambda times mu minus mu is 1. So this thing is an e-variable for one outcome. Okay? And now if you have n outcomes, you simply multiply these e-variables. That will be your e-process. And now the idea is that if the mean is 0, this thing we know by Wills inequality, the probability that this product will ever get large is very small. Probability that you ever reject larger than 20, smaller than 0.05. But if the null is not true, if the mean is not 0, then you hope by, if you have selected lambda in the right way, that this will actually grow exponentially fast, and then you will reject the null very fast. And this is actually what happens if you do things right. And again, we will see later how to pick lambda. But in a nutshell, what you can do here is learn lambda from the data, or also be kind of pseudo-Bayesian about the data. You can put a prior on lambda, and then define posteriors and predictive distributions, just like a Bayesian would, but it's really not Bayesian at all, because there's no Bayes theorem here, because what you're going to do, you're multiplying e-variables here and not likelihoods. So that's not something Bayesian, but still there are many analogies to what a Bayesian would do. So the lesson here is that e-values are generalizations of, well, Bayes factors are already generalizations of likelihood ratios. If the null is simple, e-values are essentially like Bayes factors, so e-variables generalize likelihood ratios, but in really complicated, if the null gets really big and complicated, they may not look like likelihood ratios at all anymore, but they still have a likelihood ratio flavor, so we really think of them as kind of maybe the proper generalization of likelihood ratios to complicated settings. You can multiply them, they have parameters which you can try to learn, etc. And now given this Wills inequality and doing e-values per outcome rather than per batch, we now have the ingredients to come with what is perhaps has been the most influential part of this new theory, which are the anytime valid confidence intervals. So recall this. So we make these e-variables by multiplying. We have an e-variable for every outcome. We make an e-process by multiplying it on our data. And we know that under the null, the probability that it gets larger than 1 over alpha is bound by alpha forever, basically. So once we have such e-processes, we can make anytime valid confidence intervals. How do we do that? Well, we need an if we have like a parameter. So this could be, for example, in our normal distribution case, it could be the mean of the normal, and we want to have a confidence interval for the mean. In our bounded mean example, it could also be the mean of that thing, and we want to have an interval for that mean. So I'm going to give as my example the normal distributions because it's more familiar to you, and it might look more like what a Bayesian would do. But it works completely generally also for the bounded mean example. So now you have a set of null hypotheses, so to speak, one for each value of the parameter, one for each mean of a normal distribution, or of a bounded, one for each mean of this bounded mean example. So this is your family of hypotheses, and you have an e-process under each one of them, which means it's an e-process if the null would be this set of distributions. For the normal distribution, just one distribution with mean theta. And then you know that you have for every theta, if you think of that theta as a null, the probability that the process, the product with the e-values for that theta gets large is small. This holds simultaneously for all theta. So now if we take our confidence interval at size n, the set of theta that we have not been able to reject, so we kind of do a race with all these thetas. For all of them, we look at the same time, does the corresponding e-process get larger than 20? And as soon as it does, we cut it out of the set. And then these are the things which remain, the things we could not reject at time n. Then clearly we get that for the actual theta which generated the data, we don't know what it is, but for that theta we get that the probability that this theta will ever be thrown out of the set is bounded by alpha. And this means that this is a valid confidence interval, right? Because the probability under the true theta, which we don't know, that theta is not in the interval is bounded by alpha. So the probability that it's in the interval is larger than 1 minus alpha, so it's a confidence interval. But it's an anytime valid confidence interval. So for a standard confidence interval, you only have this. You fix n, and then you say the probability that theta is not in the interval at time n is bounded by alpha. But here we have the probability that there will ever be data such that theta is not in there is bounded by alpha. So it's a much stronger statement. It's anytime valid. Again, you can continuously monitor. You can look at any time you like, and then decide and then check if theta is in there. So how does that look like? Let's do the z-test again. So we're again in this normal. We want to learn the mean of a normal. It's kind of the simplest example. So the standard confidence interval, which in this sense, in this case, is also what a Bayesian would come up with a very different interpretation. I'll get back to that in a moment. But for now, think of it as the standard interval. Just how do you do confidence intervals? You take the MLE, the average of the data, mu hat, and they do plus or minus the 1.96 over square root of n, which we've seen in the beginning of this talk, right? That's where you reject null and if the mean would be 0. Now, if you make an anytime valid confidence interval, you can actually do that using a base factor. And we've seen it before. Here we have a simple null, so we can make a base factor. I will tell you in a moment what prior we take. But let's say we take a standard prior to do that. Then we get this, it gets a little bit wider. You get a log n, a square root log n factor here, a square root log n factor here. So your interval blows up. That's essentially the price you pay for anytime validity. So there is definitely a price. You have more uncertainty. So how does that look in a real simulation? So here I sampled from a normal distribution with variance 1 and mean 7. This is the true distribution. And this is like one run where I got more and more observations in time. And yellow is the standard confidence interval. And blue is the one with this square root log n, the anytime valid interval. So you see this is like this extra uncertainty. That's the price you pay here. Yeah.
I see here that the confidence interval is positive, and I mean between 6 and 8, right?
Yeah.
And my question is a little bit out of the story, but what if the confidence interval contains 0? I know that we don't expect, we consider it as a non-valid confidence interval, right? But in many cases of the treatment response causal modeling, we see that the confidence interval contains 0. Is there any
I'm not sure what you mean by because here 0, it could contain 0, right? It's possible. That would not be. I mean, you would of course have. If the data really comes from 7, then it would go out very. Okay, well, let's say if it contains 0, then I think it just contains 0. There's nothing you can do.
So it means that we are not sure about the effect. Or we can ignore, for sure say that there is no effect of the drug, for example, the treatment effect. And
I think the first, but it's a bit orthogonal to the e-value. I mean, I'd be happy to discuss further, but I think this is kind of a different question.
It's a different question, actually, but I
because
was thinking
I know exactly what you're talking about now, and this is a very difficult question. But I don't, it's really tricky. I think formally speaking, we cannot exclude the effect of 0 if it's 0 is in there, even if we want to. But
maybe we can talk later. Thank you.
So you see that in this run, so you have a wider interval, which maybe you say is bad, because you want less uncertainty, but the truth is always in there, which will happen if you would repeat this run. It would happen at least 90 of the 20 times that it would remain in there forever. Whereas in the yellow interval, it's every now and then, it's not in there. Actually, you can show that this is around 5% of the time, if it's a 95% confidence interval. If you keep sampling, then you will lose coverage around 5% of the time. Now let's say in a bit more detail, like how we made our interval. So probably some of you, or hopefully maybe even many, know that if you do the learning the mean of a normal, then if you would do this in a Bayesian way, and you plot the 95% posterior credible interval, so it's the 95% posterior probability left and right of the posterior mean estimator, you get something which looks very similar to a classical confidence interval. And if you take a non-informative prior, basically you take a normal prior on the mean where you let the variance go to infinity, you actually get exactly the same. You interpret it differently, but it is the same interval. So a Bayesian, this is really special to normal distributions, gets intervals which look the same as a frequentist, just a 95% posterior probability. Now, I got this 6 plus log n by taking that same prior. So I basically took the base factor here for my e-process definition, and I took here a normal prior and let the variance go to infinity. And then I get this. Actually, it's 5.99 something, so there's no magic in the number 6. So that's what I did. And that would also be kind of a standard way to do it. So you see that even though we use priors, just like the Bayesians, we get different intervals, which makes sense because we have to be anytime valid, right? We have to be valid even if our priors are incorrect. So it's kind of normal that the end result looks different, but we do use priors as well. That's important. But so then what is really the difference? And this is, again, this is like the fourth thing, which is really, really important, I think, to understand. If you understand this, you understand a lot about what is the difference between what we're doing and Bayesian statistics. So we need a prior. But I said, you get this anytime validity no matter what prior you use. So how does it work? Well, the way to see that is to look at what happens if I have if I use a bad prior, like if I'm a frequentist, that just means that it puts a lot of mass very far away from the truth. If I don't want to be frequentist, I can just say I'll use a prior, and then I look at the data, and the data really contradicts the prior. You see something which the prior says is basically impossible. What happens in that case? So let's say I simulate data from mean 7, but I have a prior at mean 0 with a small variance and not a very high variance. So that prior really thinks the mean should be close to 0. And now I'm going to draw the same picture again. And now you see it's going to look completely different. So the Bayesian interval is now again the yellow interval. And so it thinks the mean is here. And it has small variance. So it's just wrong in the beginning. If the data actually comes from here, you have a very high posterior after a few data points still that the mean is here, even though the data contradicts it, because your prior is very fierce about that. But then slowly kind of you recover and you go in the right direction with your interval. Now the anytime valid interval has to be anytime valid. The only way to be anytime valid if you use a bad prior is to be very wide. And that is exactly what happens, automatically, right? I did not tune anything. This is just what happens if I plug in that prior and do the same simulation. My interval just blows up. So basically, what happens is I use this base factor to check if I can reject a null. And there are just many, many, many nulls I cannot reject for small samples, so I get a very wide interval. So that, in a nutshell, is kind of the difference, and it also shows how you can use priors and still be valid in a frequentist way. So you use them in what people have called as luckiness functions. Like if you're lucky, your prior aligns with the data and you get narrow confidence intervals. If you're unlucky, so for Bayesian, a prior is a belief, and for us, it's more like a pragmatic thing. And if you're unlucky, it leads you to wide but still correct intervals.
Can you then enforce being lucky by just looking for the best prior that minimizes based on the data? And
well, you could be kind of
interval?
worst case, least unlucky. And that's in a way what we did there in the previous prior, which is again, this infinite variance prior that makes sure that you will never be very unlucky. But you cannot be as lucky, you cannot guarantee to be as lucky as a Bayesian would be in a way. That's there's always, in the worst case, you will always be a bit wider than a Bayesian.
So the prior is still, you cannot choose the prior based on the data you've seen? No. Okay.
Okay, there are some cases where you can, but that's very mysterious. We don't understand when you can and when you cannot. It's like empirical based stuff, and it's complicated. So, but let's say you can't. That's. So I won't have time to explain to you what an e-posterior is, but it turns out you can really kind of build a whole theory on that and say there's base posterior, and then you can make another object which is an e-posterior, which is always wider. And sometimes it is much wider in order to be right, and in other cases it's just slightly wider. And it also solves something which, if you see in the literature, people trying to bridge Bayesian and frequentist inference. There's Jim Berger, famous Bayesian, and even before that there was Kiefer. He came up with this word luckiness. That is kind of what it does in a way. Okay, so then there's one more thing I need to tell you before I go a bit more in details about betting and so on. It's like, how well does this work? So we've already seen that there's a price to pay, which these intervals get wider. Even in the case where everything was correct, as compared to frequentist who doesn't use priors, by being anytime valid, we get the square root log n extra factor. You can actually play around with that by playing with the priors, and you can actually get this down to log n, which sounds very nice because log n is almost nothing. But then there's a constant in front of the log n, which makes, in practice, it's not better. In practice, we use the log n thing. So there, no matter how you do it, there is a certain price. If you look directly in terms of testing, then you see that it's really subtle, because actually there is a price, but there's also not always a price. And sometimes you actually do even better than with classical methods, because you can stop whenever you like. And sometimes you're lucky with the data, you can stop earlier. And if you take that into account, it gets really tricky. So what we do here is, again, we test whether, let's say, the mean of a normal is 0. And so the z-test. And now we compare it to, well, forget about this, an e-value based test. That's just the test I just showed you. So what medical statisticians usually do is they think of a certain alternative, which is often very fuzzy, but they say, let's say my minimum interesting mu is 1, and then they look at, like, how much data do I need to have a power of at least 80% to get there, like a certain sample size, so that the probability of a type 2 error is smaller than 0.2. The probability that I reject the null, if the null is wrong, is indeed 0.8. So we take our classical Nyman-Pearson sample size, which is what a medical statistician would use to get power 0.8. And now we look at what is the sample size we need to get power 0.8 if we do this e-value test. Where you do the test you just saw with this, which had this log n wider confidence intervals, if you look at it in terms of confidence intervals. Then you see that if you do fixed sample size testing, it's actually quite bad. Maybe not if you are in AI and you have a lot of data, but bad if you're in the medical world and data is extremely expensive, because you need about 2 times as much data to get power 80%. Right? So you would need to reserve a lot more. This gets better if alpha gets smaller. Actually, in the limit for alpha to 0, it becomes 1, but it's the same amount, but alphas we typically use, it's still like substantially more. However, what you can do here is, because this is really an e-process, if you really, if you're like in the medical world, you really want to reject this null, then you can stop as soon as your product has gone larger than 1 over alpha. That's allowed. You still have to have 1 error guarantee. So now you can say, okay, let's do that. I'm going to just sample until I get larger than 1 over alpha. Or I've reached some predetermined maximum, because I don't have infinite money. So I need to say in advance, like, I have this kind of worst case sample size where I'm going to stop anyway, but I might stop earlier, but I never stop later than that. And then the question is, what is the worst case sample size I have to set to get power 80%? So to have the same power as a Nyman-Pearson statistician. So if an effect is there, I want to have at least 80% probability that I find it. Then it gets interesting, because the worst case you need is around 1.5 rather than 2 now. So you still need more. You need to reserve for more patients. It's about 1.5. So we also did this with many other models, and it seems to be we're always in this ballpark, a bit more, a bit less than 1.5 times the data a classical statistician needs to get the same, with a fixed sample size, the same data. But that's the worst case. If you look at our expected sample size, that's like, when do we expect to stop? It's actually less than the classical statistician needs. So in the worst case, we need about 1.5 times as more, but on average, we need less. Not much less, but slightly less. And this really then that depends on the setting. Like with the Z-test, we need maybe like 95% of the data, and with this bounded mean, we actually need a lot less data. So it really depends. So if you do optional stopping, it suddenly gets competitive with classical testing. But there is this problem, and I think this is one of the major reasons why e-values are not big yet in the medical world, is that if everyone would use this, the world would need less data, and the results would be a lot more robust, because then the law of large numbers would kick in, and the averages would determine, like the average number you need before you stop would become what you actually need before you stop, because many people would work with these samples and stop, and so the averages would count. But if you're an individual research group and you ask for funding, you have to tell the funder what you need in the worst case to get power 80%. And that's really how it works in the medical world and also in psychology and so on. You have to, if you want to get money, you have to say, I plan my study to get at least 80% power, so I need so and so many participants. And there you always need more. So it's a typical thing that economists have written a lot about, the tragedy of the commons. Like for every individual, it is the best to do one thing, but if they all would do the other thing, it would be better for everyone. That's, I think, also something which happens here. And actually this also, if I can go back a little bit to this picture, where the other one, this one. You could actually, not sure if I see it here. Yeah, you can actually also, you cannot see it in this picture, but in a similar, sometimes you have a picture where, you could probably see it here. So for example, this value, it was already rejected here, right? Here it was already put out of the set. And we know that once it's, the probability that if it's true that it will ever get rejected is small. So we could actually, we don't have to include it anymore. So actually we could kind of make a line here. So what's the, actually it got even until here. So we could actually make a line here. Because we have already rejected all of these. And then we get narrower confidence intervals. And this is a valid thing to do. So in that sense, you could also make these confidence sets a lot narrower, and then they would, in some cases, be actually narrower than the classical ones, because everything that's kicked out never gets back in anymore. However, it becomes very different. I didn't show that because it looks ugly, but you can do it, and here is a little interesting anecdote. So there's this company who uses these things. They were really pioneers, called Optimizely. And so the narrowest confidence intervals you get by this, by kicking out everything and not letting it get back in which has been rejected. And then you get really competitive with Nyman-Pearson confidence intervals. But then customers come with data, and of course this data is not really IID. They may think so, but effects change over time. And if they do that, they often end up with 0 with confidence intervals. They reject everything. Because if the true parameter changes over time, that's what will happen. So they don't do that anymore, even though it would actually be the correct thing to do. I mean, and the correct answer to their customer would be like, yeah, well, none of your parameters is correct. But of course, the customer doesn't want to hear that, so they don't do that. But formally, you can do it.
Yeah, thank you. My question is, so this picture is kind of an autoregressive. So the figure that we see on the time 150 is conditionalized to the figure that we see at time 50, right? In some sense.
Wait, the data are IID. But it looks, you see dependencies, of course, because this is a function about the averages. And of course, the averages at one point depend mostly on the past. So therefore, it looks like autoregression, but it is, the data itself is IID here.
Exactly, but the question then is, probably we can design the order such that the tube will be narrower, faster, or something like that. So I think that the figure depends on the sorting of the data. And if we can do sort, then it means that our data becomes not an ID anymore, if we can sort in some sense.
Well, you can. The thing is, you're not allowed to sort it. That changes things. This is actually a rather complicated issue, but if data comes in sequentially, and then you sort it after the fact, that's that would be a form of e-hacking. That's not allowed, because then you can put it in an order where you probably always reject the null, or always get the muse you don't want to be in your interval, you can kick them out. So you're not allowed to do that. Then it doesn't work anymore.
So the assumption is that time and data are independent somehow, or what is the assumption?
The assumption here is that data comes in sequentially, so that it's a random process. So that means that there's a real notion of time, and at every time point you just don't know what will happen in the future, which you can formalize in terms of filtrations. So you can make that formal as a probabilistic assumption. What you can do actually is, so that makes it really complicated. If you, I guess for those of you who know Bayesian statistics, if you have you see the first n points, if you permute them, then at that point you will always get the same result, because it's exchangeable. So the base factor remains the same on exchangeability. So you are allowed basically to change the order if you look at the point where you're looking at now, but what you're not allowed to change the order and then look back as where things happen back. So the end result is the same, but the intermediate results you can make them as extreme as possible in the beginning, and then less and less and less extreme if you want, and you always end up with the same thing. So it's quite complicated actually, what you are allowed to do and what you're not allowed to do.
Thank you.
Okay, so maybe this is a point for having a break. Yeah. Okay. So then I'll see you soon. Yeah. Yes. Oh, you have one more question? Yeah.
Yes, I would like to ask a question if possible. Could you maybe comment a little bit more on the construction of the variables? So you showed a particular test for the mean whenever the data is bounded. But how do you actually construct that function, or how would you go around constructing that function?
I think I can show you. Wait, it was somewhere. So it's this, but of course, can I write here?
But I mean, even in a more general sense. So in this case, you're building it with something like base factors.
Yeah, and in this, and then there was the other case where I had this 1 plus lambda thing.
Exactly, but then I'm asking even more general. So if I don't want to go for the base
So I will get to
factors.
that. There are a few guiding principles, and there's not one kind of, not like this is the way, but there are a few ways which make sense.
Okay.
Yeah, I'll get to that after the break. Yeah.